Hi, and welcome to Advanced Machine Learning. I'm Victor Banks, and right now we will take a look at the analysis for the follow the leader algorithm for online quadratic optimization problems. So previously we had the following statement. So first of all, we specified what quadratic optimization problem is in the online learning world. So it's essentially characterized by the loss function, which is nothing else than the quadratic loss function. And in its most general form, where we have the case that the action space and the environmental data space are simply subsets of RD, it is given in the following way. So it's the distance in Euclidean norm between an action performed by the learner, AT, and the corresponding environmental data point we obtain for this case. And the follow the leader algorithm already satisfies a quite satisfactory theoretical guarantee in terms of its regret for this case. If we assume that the environmental data space is such that the largest environmental data point in terms of its Euclidean length is of length v. So v is some constant. And to make life easier, we also assume that the action space is RD. We can also take a look at real subsets, but then we have to go to projections where we in fact also get the same theoretical guarantee as we will show right now, namely that the regret for the follow the leader algorithm for a time horizon capital T is bounded by some essentially logarithmic growing function with respect to the time horizon capital T. Okay, so to make life easier, we will denote the sequence of the actions taken by the follow the leader algorithm without the superscript. We know right now that we are dealing with the follow the leader algorithm. And remind ourselves with our short-term memory box here about the useful lemma we have shown, namely that the regret of the follow the leader algorithm till capital T, till the time horizon capital T is reached, is bounded by this difference of two cumulative losses. The one is the cumulative loss of the follow the leader as it is, and the other is the cumulative loss of the cheater version, which already knows the current environmental data point. And if we have this useful lemma, we can boil down the assertion we want to show that this inequality holds, because what we have here is, we know the regret of the follow the leader algorithm is bounded thanks to this useful lemma here by this. And if we can show now that this upper bound for the regret is in turn bounded by what we want to show. Now this is this logarithmic growth of the regret, then we are done. So all we need to show is this inequality 1, thanks to our useful lemma. And what we will do is, first of all, we will derive an explicit form for the actions taken by the follow the leader algorithm. Previously we saw already that this will be the empirical average, so we motivated it with the supervised learning scenario, where we know that for empirical risk minimization without an instance space, we know that the learner, the best linear model in this case for the quadratic loss function, is essentially the empirical mean. And now we can also verify this for the follow the leader. Yeah, so the claim now is, well, the action in time step t is nothing else than the empirical average of the environmental data points seen so far. And this is of course due to the fact that we are dealing with the quadratic loss function, which for sake of convenience we state here again. Okay, let's see how we can show this. So let's recall how we have specified, or how the follow the leader algorithm rather chooses its action in time step t. So the action in time step t is the action, so here we have now an equality instead of the element. Yeah, so again, to make life easier, it's the element in the action space which is minimizing the cumulative loss among all actions for the data seen so far, for the z's we have seen till time step t. Yeah? And this includes z1 till zt minus 1, because the one in time step t we will only see in our basic online learning protocol after we have carried out this action here. Okay, let's plug in what the loss function is. It's the quadratic loss function, so this here is simply inserting the definition. And well, what we have to do in order now to find this minimum here, is essentially we specify this term here, this cumulative loss, this cumulative quadratic loss to be more precise, as a function of a which we want to minimize. Yeah? So we seek to minimize this function f with respect to a over the action space. All right, so the Euclidean norm, or rather the squared Euclidean norm, can be expressed as the inner product of the vector with itself, which we have there, and the vector we have here is a minus zs. So here you have inner product of a minus zs with a minus zs. Okay, and we can compute the gradient of this function. So what's the gradient of this quadratic function here? Well, it's nothing else than a minus zs. So we can do the computation of the derivative for each summand separately. So because here we have this sum structure, we can do this separately for each summand. And if you do this for each summand, the gradient of each summand is a minus zs, simply because gradient of a minus z transposed, this is 2 times a minus zs. Now, so if you want it more precisely, this here is a transpose a minus 2 times a zs plus zs transpose zs. So you can compute the term more explicitly, and then you see, well, this here is independent with respect to a, so this will be a 0. This here is a linear function where the transposing here is missing. This is a linear function, so here the gradient will be only, so with respect to a will be minus 2 times zs. And here we have a quadratic term where we will get 2 times a as the gradient with respect to a. And this is then in line with what we have here, because the 1/2 is cancelling out with the 2, which is appearing here in the quadratic and the linear term. All right, and then if we now set this gradient to 0 and solve with respect to a, this can be done by first rewriting the gradient as follows. So we have that the term in the sum, this one here, the a, is not depending on the s, so we are essentially t minus 1 times summing up the a, and well, the remaining part is as it is, remains as it is. It's minus the sum over the environmental data points. And now we set this here to 0. Solve it with respect to a, and well, what do? We bring the sum of the zs on the right hand side, divide by t minus 1, and well, we end up with this form for the a, and this is indeed minimizer because the function f we are looking at is in fact convex, so we have already found the minimizer if we look for the critical point. So computing the a, which has a gradient of 0. Okay, so we have here verified that indeed the action taken by the follow the leader algorithm in time step t is nothing else than the empirical average over all environmental data points seen so far. Now, since we know that the action is now the empirical average, we can also show that with this knowledge we can have a very cheap update formula, which will be also of use for the remaining proof. So if we know AT is the empirical average, then, well, AT plus 1 will still be the empirical average. Yes? So we are only one time step further. And this means that AT plus 1 is nothing else than the sum over all environmental data points seen so far, so including time step t now, because we are in t plus 1, and then dividing by the number of data points, which are t. This sum here in turn can be rewritten into the following form. So we simply sum only till t minus 1 all environmental data points and put them in one closed sum formula, and then add the last one. Because of that, so why did we do this? Because now what we could do, we could multiply here with the 1. And which one can we use? Well, we can multiply here with t minus 1 divided by t minus 1. And now if we ignore the t minus 1 in the numerator, we see, well, what do we have there? We have simply the empirical average over the environmental data points till time step t minus 1. But we know AT is the empirical average of them, so this is equal to AT. So we can also write it in a more convenient way, like this. So 1 over t times zt plus t minus 1 and then AT, which is the empirical average of the environmental data points seen till time step t. Okay, then, law of distributivity, we can multiply this 1 over t with zt, get this one. We can multiply this one with this one, and this simplifies to 1 minus 1 over t, and the whole thing multiplied with AT. So what we see from here is a quite cheap update formula, because all we need to do to update the next action, to specify what the next action will be, is divide the current environmental data point by 1 over t, multiply the previous action with 1 minus 1 over t, and this is giving us the next action, which is again nothing else than the empirical average. But you see, we have here indeed a quite update formula, because it's exactly of that kind as we want. It's essentially only depending on the most recent environmental data point and something we need to store anyways, namely the action we used before. All right, now for our theoretical analysis, we will further rewrite this equality we have here. So we can bring the zt on the other side, or rather we subtract on both sides with minus zt, and well, if we subtract on both sides with the minus zt, we have here on this side that we have to subtract the minus zt, and then, well, if you look closely at this formula, you can conveniently collect it into the following form, where we multiply it with 1 minus 1 over t, and then with the minus zt. This is due to, we have here the minus zt with a factor of 1, and the 1 over t is with the positive factor which we get if this and this are multiplied. All right, so with this we will show the following bound on the difference between the losses of the follow the leader algorithm as it is and its one step look ahead cheater version. So because this is essentially all we care for if we want to show our claim, where we just sum up all these differences, and if we can say something about every single difference, which will be this year, we have the hope that we eventually get something which is interesting, and this will be in fact the case. All right, so let's again put something in our short-term memory box, namely this convenient way to express the difference between the action in time step t plus 1 and the environmental data point in time step t in this way. And now we can show the claim we saw before in the previous slide as follows. So let's plug in the definition of the loss function. So again, what is our loss function? It's the quadratic loss function, where we look at 1/2 of the difference squared Euclidean difference or distance between the input, A and Z, action and environmental data point. And this is essentially what we use here with the two respective pairs we have there. So AT and ZT and AT plus 1 and ZT. Okay, and then what we can do is we can get rid of or use the law of distributivity, use this 1/2 and this minus 1/2 and write it in front of it, that we have the remaining two terms, this squared Euclidean distance terms collected in one bracket. And then we can use actually our convenient way to express the difference between action in time step t plus 1 and minus ZT here, and get this here. All right, and now from here we can go further as follows. So we have the difference between the losses here is equal to this expression, Now we can further manipulate this expression here, and we will start by using this 1 minus 1 over t expression, that this is simply a scalar, which we can plug out or pull out of the squared Euclidean norm here, and we have to be careful and not forget that we have to square it. But this is essentially what was done here. Okay, and then what we can do is we can take a closer look at what we have here, and voila, we have here 2 times the same term. And again, we can use the law of distributivity. So here we have a factor of 1, here we have the factor of minus this squared term, and we can collect it into this term. And now with a bit of binomial formula calculation, we see if we calculate this here more explicitly, we arrive at the term 1 over t minus 1 over 2 times t squared. And this term, in fact, this is always smaller than or equal than 1 over t. Yeah, why? Because here we subtract something which is non-negative. Yeah? So 1 over 2 times t squared, this is always non-negative. Yeah? So the entire term here, this 1 over 2 times t squared, is non-negative. And if we forget about it, we only make the overall term larger. Now this is what we get here. And this is exactly the claim we wanted to show, that the difference between the losses of the follow the leader algorithm and the one-step look-ahead cheater version is bounded by the difference of the action and the ZT in terms of squared Euclidean norm and multiplied with 1 over t. Now let's put this also in our short-term memory box, what we just have shown, this difference here between the losses of the follow the leader and the follow the leader one-step look-ahead cheater version. And now our assumptions come into play, namely the one that we have that the supremum, so the maximal length of the environmental data points we have are at most L. So if we know that the empirical AT is the empirical average over the data points, the Euclidean length of this empirical average cannot be larger than L, because all of them here are having Euclidean length at most L, and if we average them, which is done by AT, the resulting Euclidean length cannot be larger than L. Now we use the simple triangle inequality, which holds for any 2 vectors x and y, which for convenience is restated here. So the Euclidean length of the sum of 2 vectors x plus y is always bounded from above by the sum of their Euclidean lengths respectively. This is what we get here. And now we use this with x being AT and y being minus ZT. So of course this is also true if we make the substitution that y is some vector multiplied with the minus 1, because this is true for any vector. And well, what we get is the Euclidean length of the action AT, which is, as we just have clarified, smaller than L, and the length of the environmental data point ZT, and by assumption this is smaller than L, so we have here this is smaller than L, this is smaller than L. We get here a bound of 2 times L. And now we do what I already hinted on. We are looking at the sum of these differences of the losses between the follow the leader algorithm as it is and its one step look ahead cheater version. We have shown that this bound here holds true, so we can use it for every summand. Yeah? So for every summand we can use this reminder here. This is what we do. Now we can make use of our triangle inequality more or less here, but we have to keep in mind that here we are squaring, but no problem because we can square this here, so we have also to square here, and what we get is 4 times L squared, or you can also leave the L squared as it is. Yeah, and this is what we get here. And this 2 times L squared term is not depending on the t, obviously, so it's a constant, which we can write in front of the sum. This is what we get here. And well, we end up with this expression that the cumulative difference between the losses of the follow the leader algorithm as it is and its one step look ahead cheater version is bounded by 4 times L squared and then the harmonic sum, more or less. Yeah? So here you see the harmonic sum. We sum up 1 over t. And now all we need to do is essentially say something about the growth of this sum here, of this harmonic sum, with respect to the time horizon. And well, it is known that this is logarithmically growing with the time horizon, or with the summation and summation index of the following kind. Yeah, so we also have to add a +1 for the very first instance, for the t equal 1 instance, more or less. And if we use this, that this and this here holds, we can apply it for our reduced term. Yeah. Remember, we have bounded the regret of the follow the leader algorithm by this sum here due to our useful lemma. And well, we just have shown that this inequality here holds true, and now we know the harmonic series is only growing logarithmically, essentially. We add here a +1, and we end up with the claim we wanted to show.